Okay, let's start. So okay, for those of you today, my audience size uh tripled. So anyway, what's what happens that we will just go through page by page. If you want me to go through a particular question, then just let me know. Okay, otherwise we'll move on lah. Okay. So along the way, I'll try to recap the key concepts that's being tested for this for that question lah. Okay. Okay, maybe I'll let you up the volume a bit and 下字. Okay, on page one, we have questions 17 and 18. If there's no issue, we'll just go through both of them. Is that okay for you? If you want, you can type and check on yourself, lah. Right? Okay. So first one here, this is a this set of nodes is on superposed wave and SHM. So this one here, this is a two source interference question. Okay, but remember for interference, you cannot just assume that everything is just based on your formula where you have your lambda equals to ax over d. Okay, it's not just about that, lah, right? There are this one is only for your Young's double slit. So this is for Young's double slit. Young's double slit. Uh, okay. So this is a special case of your interference. By most cases, right, your interference will be just as simple as having two sources like this. You have your source X and source Y, right? They are traveling towards the same point, right? And then they will meet at that point, and then they will basically interfere with each other lah. So for this kind of question, right, you need to go back to the basics to go and count, like in terms of wavelengths, right? How many wavelengths you have, etc. Then go and see whether they're in phase or out of phase. All right. So here they tell you that okay, they actually don't need you to calculate what is the amplitude and all. They just want to find the phase difference. So they give you things like okay, they told you the two waves are in phase at the start. Okay, the two sources are in phase. That's very important. It means when they start off, right, they are starting off together. Okay, like that. Say like that. Okay, and face with each other. All right. On I mean total basis. Okay, then they tell you the frequency is 0.4 hertz. Okay, then now the key information is that source X takes 3 seconds to arrive, source Y takes 3.5 seconds to arrive at P. Okay, so you will know now you know that Y is further away from P, right? And Y will take a longer time to arrive. Okay, that means they arrive out of phase. Okay, how you can basically work out the phase, the time difference now. The time difference now is basically your delta t, right, is just 3.5 minus 3.0. So you get 0.5 seconds of time difference. All right. And once you have time difference, you can work out your phase difference quite quickly. Okay, phase difference, you just need to basically apply your formula. Remember this formula here, right? Your phase difference formula, there are two forms. This is in terms of timing. Okay, so this is delta t over period times 2 pi. Okay, another form. Okay, let's just work this out first. So this is 0.5 over, okay, they never give you period, right? They give you frequency. So just invert your frequency. So 1 over 0.40 times 2 pi. Okay, so this will give you your phase difference. Okay, and another formula for phase difference, if in terms of wavelength, right, you can also have delta x, the path difference, divided by wavelength. Okay, multiplied by 2 pi. This will also give you your phase difference. Okay, if you are given in terms of wavelength. All right. So it's question 17. Any issues for 17 so far? Okay, quite straightforward. Okay. You should be able to calculate. Okay, amplitude is a bit hard to calculate because it's not in phase lah. Yeah, you don't really know the wavelength, so it's a bit hard to calculate amplitude. Okay, but if let's say your phase difference is in nice multiples, or let's say like pi, right? Then you can work it out lah. Okay. All right. 18. Okay, 18. We have a diffraction grating. All right. So remember for diffraction grating, this is also basically interference. right? When we do a two source interference, you're working with two slits, okay? And your diffraction grating is essentially you have much more slits than that, lor. Okay, so remember for two source interference, right? We will have a pattern that is okay. So let's say your screen is here. You have two sources here, right? What happens is that each of them will give you its own peak, okay, its own diffraction pattern like this. Okay, so you will form diffraction pattern like this, so on and so forth. Then you have another one that is centered here. Okay, forms another pattern like this. Okay. So when you have your two source interference, like, is these two patterns coming together to give you one large pattern at the center like that. Okay. This is how you get your two source interference pattern. Okay, for once you start having more sources, right? What you do is that you end up having, if you have if let's say you create one more stick here, try to create more stick here for you. Hold on. Let's try to make one more stick here. Okay, let's do one more stick. Okay, so we can do like that and then like that. Okay, so if you do this, right, you have one more pattern forming up. Okay, and the more sticks you add, right, you have more patterns forming up like this. Okay, and basically what you end up with is that your pattern become very neat. It will be quite uniform. So let's say you have multiple sticks here, right? This is your diffraction grating, right? What you have is that you end up forming, you have a central one, and then the rest are all quite evenly defined like that. So this is what you have, right? When you form your diffraction grating. And then of course diffraction grating, the formula is quite straightforward. It's just d sine theta equals to n lambda. Okay, there are some limitations here. This one cannot be larger than 1. Okay, very important. This d, right? This is basically in terms of meters, the slit separation. Okay, so usually they will give you in terms of number of lines per mm. Okay, they need to make sure you convert it correctly. So 500 lines per millimeter, you have to convert it to 500 times 1000. Then you get 500,000 lines per meter. Okay, so let me just add one page here so that we have a bit more space to work with. Hold on, Okay, so let's go back to the correction purpose here now. We have monochrome light falling on diffraction grating and normal incident angle. Second order diffracted beam occurs at angle 31 degrees to the normal. What's the maximum total number of intensity maxima that we can see from the grating? Okay, so we can sub this into the formula. Let's write the formula first. So let's put it here. So we have d sine theta equals to n lambda. Okay, what can we sub in? We can sub in theta and then we can sub in n. So we have d sine 31 equals to n, equals to 2 lambda, right? Sorry, these are the 2. 2 lambda. Okay, like this. Okay, then now we can, before we move on, let's look at what we're supposed to find. We want to find the number of intensity maxima. Okay, so that means the number of bright fringes I can see on one side. But remember, if I take the center line here, let's mark out the top center line here, this center line here, right? Okay, this is a central maxima, right? If my n is 3, right, I will count 1, 2, 3. But there's also 3 on the other side, 1, 2, and 3. Then of course the center 1, 0. So total here there are 7 maxima here, right? Okay, so be careful how you count them. Okay, so let's see what you're supposed to find. Okay, we write the equation again, the d sine theta equals n lambda. We're going to make sine theta the subject. So sine theta equals to n lambda over d. Okay, I cannot let my sine theta be larger than 1. Okay, so if I write nicely, n lambda over d. So this is the ratio that is important. Okay, I want to, first I need to know what is lambda over d first. Then I will sub in a value of n that does not allow the sine theta to go more than 1. Okay, so let's try to work towards that structure on this side, on the other side. So what I have on the other side here is that we have this d sine 31 equals to 2 lambda, right? So we're going to rearrange this guy. We're going to make lambda over d the subject. So we're going to have sine 31 over 2 is equals to lambda over d. Okay, then let's pop up the calculator for a while. Okay, so calculator, right? So I'm going to work out what sine 31. So we do sine 31 divided by 2. I get 0.257. Right, so back to here. So lambda over d is equals to 0.257. Okay, I'm going to take this number. I'm going to plug it into this side here. Right. Okay, then I realize I will have, this will become n 0.257. Okay, which means my n, the largest number it can take is 3. Cannot be larger than 3. Okay, so you see a total of 7 bright fringes. Okay, because if you go 4, you go beyond 1 already. If you sub 4 into here, right, this whole term will become larger than 1. So you don't want that to happen. Alright. So you go for n is 3 lah. That means you see a total of 7 bright fringes because just nice this diagram. So you see 1, 2, you see central, 1 on either side, 2 on either side, 3 on either side. So the total see 7 in all. Can? Anything you want to clarify about diffraction grating? Okay, since we are talking about diffraction grating now, you can type lah. No have Okay. Moving on. Do I need to talk about 19? 19 got demand. Don't have 19. I skip Okay, skipping 19 15 and 16. Okay, sorry, 19, I just go back and share one tiny point. Your tuning fork, right? Remember for tuning fork, it's always a constant frequency. Okay, I believe you've done an experiment with tuning fork. So tuning fork, different tuning forks will give you different frequency. It's a constant frequency. So the wave that it pumps out, right, is always the same. Okay, so basically what I'm trying to do is that you are trying to, if you draw the wavelength, right, if you draw a stage wave inside here, there, right, you're basically trying to find ugly line. You're basically trying to find the point, right, where let's say if you want to have a resonance, right, you need to have this is a close pipe, right? You need to have it such that your water level is here. Here, the next one will be at here. Okay, so on and so forth. Okay, next one will be somewhere below lah. Okay, when it is at the node. Okay, so that's all I say for this. I think you can try on lah, no problem. 15 and 16. Any demand? 15 and 16. Okay, can. Look 1, 15 and 16. Okay, so you come online because you have tried the question, you got things to ask. Okay, so don't if no one asks for you, then you ask. Okay? If not, you're just not maximizing your time here as well. Right. 15. Okay, 15. Which topic is this? Anyone? Is it still waves? 15, 16, 17. 17 is the next one. Okay, can. Yeah. Which topic is this? SHM. This is a SHM question. So, okay, usually for MCQs, right, the questions are arranged in the right order one. You will hardly find a case where your question is in the wrong. Okay, the right order is in following the topic, right? It should follow that order. Like 99% of the time. Even their changes are usually just within like closely related topics like COE and DC, maybe Because like some it's very hard to draw the line between COE and DC, where COE stops and where DC begins. So sometimes you might find there's a bit of overlap, but otherwise, right, the questions will kind of follow the flow of your syllabus. All right. Okay, so here we have SHM, you have particles oscillation, then you have this graph here, you have a displacement time graph. Okay, so let's quickly recap some of the SHM formula. I think it's good to just quick recap of the formula for SHM. Okay, remember for SHM, your basic formula starts from your A equals to negative. Okay, the basic idea is your acceleration is always proportional to negative of your displacement from your equilibrium position. Okay, then we go on one more step to say, oh, A is equals to negative omega square x. Okay, so this one here, I need to stress that this guy here, this A, right, is not a constant. This A is a function of, okay, I go use math notation for this. This is a function of x. Okay, I think that's how you write it, right? Okay, this is a function of x. Okay, then if you want to have maximum acceleration, right, you have max acceleration where it's called a naught, right? A naught is occurs at negative omega square x naught. Okay, so in this case, this is a constant. Okay, these terms here are constants. Okay, so you sub in. That means if you want to find the maximum acceleration, right, you sub in the displacement, right? Okay, then from here, right, you can work out a few other formulas. I will not go into derivation today. Okay, but you can basically go and find out how to find the velocity, right? So V equals to okay, the one that's based on your displacement, right, will be what's formula? I can't remember. There's x minus x not involved, right? Crap, I can't remember formula. Wait, somewhere anyone? Minus omega x naught, right? So this is omega x naught square minus x square. Is it correct? Is my formula correct? I can't remember, seriously. Plus minus, there's a plus minus term in front. Formula sheet. I take a look. Do I have formula sheet anyway? Easy. H2. Jesus. I look at formula sheet again. Sunny can't remember formula. Okay, you will say I'm correct. Okay, so it's correct lah. Okay, so again, this one here, this is a function. This is a function. This is not a constant. Constant one is V naught equals to plus minus omega x naught. Okay, but the thing about this is that, okay, if you look at this line here, right, this one here, right, you want to get the maximum velocity, right, your x has to be 0. If your x is 0, then this whole term becomes x naught. Okay, so that means this is the part that's a bit confusing. If you look at this formula V naught equals to plus minus omega x naught, right, you might be tricked to thinking that, oh, your maximum velocity happens at your amplitude x naught, but it's not. This is the constant. Okay, so to find the velocity at any point in space, right, you use this guy here. Okay, then from here, right, of course, you also have the other forms. Okay, then from here, you can talk about, I think this question about kinetic energy, right? Let's, don't have, okay, I might as well talk about the KE here first. Okay, I'm going to squeeze some stuff on top here. Okay, then of course, we have your energy. So because we know that, KE, right, is equals to half mv square, right? So if I take the equation from bottom, this becomes half m omega square x naught square minus x square. Okay, so this gives me the maximum KE. All right. So this gives me the KE. Again, this is a function. function of, this is a function that gives you the KE at a particular position. Right, then we want to find maximum KE. KE max, right, is just half m omega square x naught square. Okay, so maximum KE occurs at where? Occurs at x equals to 0. We very careful about this. Okay. Where's my screenshot? Okay. Right. So that means the other kind of energy is potential energy, right? So because this, when your system comes to a complete stop at your amplitude, right, your KE will become 0. So maximum PE max is also equals to the same value, half m omega square x naught square. Okay, this is the maximum value of PE. Okay, from there you also can find PE based on position. This is a function again. PE based on position is half m omega square x square. Okay, so these are the few things I'm dealing with. Okay, but of course, SHM can also be represented using the timing here as well, lah. Okay, so timing here, this one is much simpler to do. Right? So this one here, this is your displacement graph. Okay, then we know that, okay, if you have your maximum displacement, right, at this point, right, V is 0. Okay, V is 0. And V is 0. Okay, how about point A, point B, point C, point D? Which one is positive maximum velocity? Which one is negative velocity? You should be able to identify it using the gradient now. Okay, so we look at the gradient here, right? This, if you remember, go back to kinematics, right? If you go and differentiate if you find the gradient of the displacement, right, you'll get your velocity. So this one here is positive gradient, positive velocity. So the V here is plus V naught. This is negative V naught. This is plus V naught. This is negative V naught. Okay. So anyway, but once since you're finding KE, right, the direction doesn't matter, lah. Okay, but now I know that within a time frame of 1 period, I will have 3 points at 0 velocity. I have 2 points with maximum velocity. Okay, so since I start off at the amplitude, right, my V is 0. Okay, so I can eliminate the graphs that is not that's not KE 0 at the start. So I can eliminate A and C, because A and C start from non-zero values. Okay. Then what does X naught? Okay, you will answer a question later with me. Okay, then you have B and D, right? Okay, so B and D, which is the correct one? So remember, we need to look for the correct number of cycles. In one cycle or period, right? One cycle here, right? I basically have 0 KE one time, then maximum KE, 0 KE, 0 KE here because you are at amplitude. Okay, so amplitude of velocity is 0. Then you have maximum KE, 0 KE again. So the best answer here is D lah. Okay, because in A, right, in B, right, you only have two points of 0 KE. Okay, X naught represents in the velocity equation. Yeah, X naught is your amplitude, the amplitude of your oscillation. So it's a constant as well. Is that okay? You will okay? Okay. 16 coherent light waves that are plane polarized, each intensity twice of the intensity of A. Okay, so let's read this question again. You have okay, so now we are talking about, this question is not about polarization. It's about interference again. Okay. So they tell you that coherent, remember, basically constant phase difference. constant delta phi. Okay, which implies that your wavelength and your period, right, same. Okay, because if you can start off two waves in phase with each other, but if the period or wavelength is not the same, right, what will happen very very quickly is that they'll go out of phase. So in phase means I will hit. So the two waves will hit will hit amplitude at the same time. They will come back to equilibrium at the same time. Okay, and they are if they both hit positive amplitude at the same time, they both hit negative amplitude at the same time. It does not concern the amplitude. The amplitude is not part of this discussion when we talk about coherence. Coherence is just a matter of maintaining the same phase difference. You can have different amplitude, but you can still have the same phase. Same. You can be in phase, you can be out of phase. That's fine. Okay. Plane polarization here. Okay. So this one is another important condition. Same plane polarized, right? Remember when we pass our light through a polarizer, right? So let's say when we do the usual one, sorry. We always draw it like this way. This is unpolarized light, right? Then you pass it through a polarizer. Okay. At the end, right, you'll get only like that, right? This is what you have. Okay. So when you say that you have the same plane, the two waves are polarized in the same plane, right? That means, right, for both waves, I'm using the polarizer in the same direction for them. That means when for both waves, right, when they pass through the polarizer, right, they will both emerge in the same plane. Okay, so it could be both like this. It could be both this way. It could be both this way. That's fine. It doesn't matter as long as the same plane. Okay, this is important because if you're not on the same plane, right, you cannot interfere with each other. Okay, so for example, if you have a wave that's polarized in the vertical plane, and then you have another wave that's polarized in the horizontal plane, right? They cannot interfere with each other. Okay, they can't superpose each other. Okay, or if you have cases where, let's say, if you have, okay, this one I need to draw. Let's say you have one source that is in, okay, one source that is in this direction. Okay, the other source that is in this direction. Okay, to superpose these two fellows, right? I need to find the vertical component of this guy. Then I superpose this one to this one. The horizontal component here, right, it does not matter. Okay, so I have to be very careful about these terms here. Okay, so they superpose at a point that is equal distance from the two sources. Intensity light at that point is twice the intensity of the phase due to either wave alone. What's the possible phase difference between the two waves at that point? So the two sources, right, they are not, you see, they at the start they never tell it's just coherent, they never tell it's in phase. So that if they are going to an equal distance, right, that means they will still have the same phase difference when they reach that source. Okay. So here you want to find out what is the possible phase difference between the two waves at that point. But they tell you that, oh, intensity is twice. Okay, twice the value. Okay, so for this, right, we need to look at the relationship between intensity and amplitude. Okay, we know that intensity is proportional to amplitude square. All right. So when we look at superposition, right, if we have an in-phase superpose, let's say let's say we have one wave that is like that, okay, and this is amplitude A, the other wave is also amplitude A. When they superpose this way, right, you will get a wave that has amplitude 2A. Okay, so 2A will mean that my energy, right, let's say the intensity is I and I, right, the intensity here becomes 4A squared, okay, which is actually 4 times of my original I. Okay, so if it's a in phase superposition, right, it means the crash to crash, right, you get 4 times the intensity. So this one, they are trying to trick you to think that, oh, this one twice the intensity means that, oh, it must be in phase. That means it has to be a phase difference of 0, 2 pi, 4 pi, and so on. Okay, but that's not the case lah. All right. Okay. So then what's the possible answer here, right? Actually, this one, if you can figure out this point, right, that it is not, because, okay, if it's in phase, right, you expect 4 times the intensity. It should not be twice. Okay, so that rules out 2 pi already. Okay, because 2 pi is in phase. Okay, so right, okay, should write, maybe right. Completely in phase. Okay, if it's completely in phase, your new amplitude, your A new, right, will become 2 times of A naught. That means my I new, right, will become 4I naught, because I is proportional to A squared. Okay. Okay. Then the next thing we can rule out is option B and D already. Okay. B, right, is a phase difference of pi. Pi phase difference, what kind of interference will you get? Anyone? Will you get constructive? Will you get partial? Or will you get destructive? That means completely becomes zero. Do you know how to draw for wave phase difference of pi? Okay, so let's try drawing that for pi. So again, let's have two waves. Okay, so first one is like that. All right, so this is just a normal one. Second one, if it's in phase out of phase by pi, right? What happens is that you shift forward. Remember, in one complete cycle, this is 2 pi. This is 2 pi. So I shift forward by 1, by half a wavelength here lah. I shift forward, right? Then it will become like that. Okay. So then we look at the interference, right? Then this interference should become, because this point, peak and trough, right, together should give you 0. Okay. And then of course we should know that, so this one, this result will give you, this is destructive lah. So this is destructive. Okay. And then 3 pi, right? 3 pi of phase difference is the same as pi of pi phase difference. So again, this is destructive. Okay. Right. Then the answer has to be A lah, right? Okay. By A, what exactly is A? Okay, so let's do for A. Let's do one more wave at the bottom here. Okay. So more wave at the bottom. Okay, I think I draw the side here lah. Draw the side here. Okay. So again, one wave like that, right? So if I'm pi over 2 out of phase, right, you shift forward by quarter of a wavelength. So you shift forward by like that. Okay. So you basically, this portion is pi over 2. Lambda over 4 lah. Lambda, what am I writing? This is, if I'm measuring in terms of wavelength, this is lambda over 4. Okay, so it's pi over 2. Okay, so we check. So that means here, if I want to find the difference, right? This interference will become like that. So your black color one, let's say it's like that, right? This is your black color one, right? Your red color one will be off by a little bit like that. Okay, something like this. Okay, so yeah, quarter wavelength. Yeah, half quarter wavelength. So this point here, right? This will not, this is less than 2A. Okay, so this will be less than 2A. So if we look at, if you have if your I new is equals to 2 times of I naught, right? If I square root to find amplitude, right, I know that, okay, so this will be A new square equals to 2A naught. Okay, that means my A, sorry, what am I doing? 4I, yeah, so it is 2A naught square. Okay, so A new, right, is equals to square root 2 A naught square root. Oh no, without square root, sorry. Yeah, just like that. Okay, so this number is less than 2 times. Okay, so this is not a completely constructive. It's not a full addition. Okay. 17, 16, right? I move on to 17, huh? Okay, 17. Okay, the second JC paper is harder. I think Luke I discovered it yesterday. So second school, if I remember correctly, is NYJC. And NYJC has quite uh good questions that are almost to the standard of the top few JCs. I would say NY is the uh best. I would say is they have the highest standard outside of the usual top JCs. So. Okay. All right. So we are 17. This is talking about stationary wave. Okay, so stationary wave quite straightforward. Stationary wave, you need to talk about your nodes. So this is your node. You have your anti-node, node, anti-node, node, anti-node. All right. Anti-node is here and then node is here. Okay. Anywhere within one pair of nodes, right? Anywhere between here, right? They're all in phase. Okay. Then anywhere in the next node is out of phase. All right. So you want to find the phase difference between two waves at point X, Y, and Z, right? Okay. So if you are at X and Z, you should be completely out of phase. Then Y is in phase. X, Y, and Z. 0 pi and negative pi lor. Is that the answer? I never checked as well. This is question 17 from second JC, right? Question 17 from second JC. Yeah, A lor. Okay, so you work by that notion. Okay, everywhere here is in phase with each other. Okay, so one is that. Can structured, we have how many questions? I think superpose I might highlighted too many questions, but yeah, I actually don't like superpose also. Yeah, a lot of polarizer questions. Okay, back to question 3. Okay, anything else for the MCQs? No, we move on to this one. Okay, if no one say anything, I'll just assume that I go through the whole thing lah, right? 3A all the way to the back. But some stuff I can go faster. I'll just show you. Let's just refer the answer key. Okay, so here I have two source interference are set up. Okay, then I have the various distances small a, lambda, and so capital D. When light of wavelength x is incident on the double slit, the separation is x. State and explain the effect, if any, on the separation of the fringes and on the contrast between dark and bright fringes when the incident light is polarized onto a single plane before reaching the double slits. Okay, so polarization does not affect the wavelength. Okay, so this remember this one equation is just lambda equals to ax over d. If you don't change your lambda, you don't affect your x. Okay, provided everything else stays the same. A and d stays the same. Okay, so separation has no effect. Do you need to explain? Explain, right? Okay, so explain here. No effect. No effect because your lambda stays constant. Okay, so your lambda stays constant, your x doesn't change. Okay, contrast, right? Contrast is a bit more interesting. Contrast is basically, okay, you will see this term very often. Contrast is a compare brightest to darkest. Okay. So, okay, I do photography, right? So I can tell you contrast you can do in few ways. Few ways are one, if you make the you make the brightest part brighter, then you increase your contrast because you are stretching out. You just think of it as a scale. So let's say you have, this is your intensity of light, right? Okay. Then your brightest is here. Then your darkest is here, let's say. Okay, if you shift the brighter up, right? You shift this guy up, right? You are increasing this spacing. Okay, or if you make the darkest further darker, then you will also increase the contrast. If you bring both of them in, then your contrast will be smaller. Okay, so when then again in photography, when you adjust the brightness of photo, right, you could be doing stuff like, okay, I shift my B up, my brightest up by some increase in intensity. I shift my darkest up as well. If I do that, right, the contrast is still the same as before. Okay, because it's a difference between the brightest to the darkest. So I need to either, if I want to change contrast, I must change the separation between them. Okay, so when I pass through polarizer, what happens first? So before polarization, right, your light comes in all directions. Okay, that means part of the energy, the energy of light is distributed to different planes. Okay, but then once I pass it through a polarizer, like this, right? So this is a polarizer, right? Okay, after that, right, I will just get single plane like this. Okay, that means all these other ones, this one, two, okay, this one, this one here, right? It can be resolved to give you vertical and horizontal lah. So, but definitely I know that I will lose this horizontal one. I will lose this horizontal one. I will lose this horizontal one as well. So all the horizontal ones get cancelled. If remember, if you want to simplify this guy, right? This guy is just basically just like that. Okay, all the diagonals can be converted into your components, your vertical and horizontal components. So that means if I pass this through your polarizer, I lose half of my energy. Okay, so that means your contrast will drop. Okay, because after passing through polarizer, after polarizer, right? Okay, half of light energy is lost. Okay, so this means that you will have lower intensity, which leads to lower bright, less bright lah, less bright fringes. Okay, the dark one does not change. So the dark will still be completely dark because this does not affect your cancellation. Your like okay, so if let's say you at first you have you have two waves of amplitude, let's say A and A, right? A and A, right? You add up, right? You get maximum is 2A, your minimum is A. But now let's say let's say you go and half them, right? I think it's square root 2 if I remember correctly, because you half the intensity. Okay, A is square root 2, right? Okay, your max becomes 2A square root 2, your minimum becomes 0. Okay, so this here, right? Your minimum here should be, sorry, I'm missing. This one should be 0. Okay, so your darkest one does not change, but your bright fringe will become less bright. So I think this one is over here. Okay, polarization causes intensity to decrease. Hence, bright fringe is less bright. Okay. Alright. So yeah, the next one is a interference correction as well. Yeah, I'm just assuming you want to talk about this. If no one, I won't know because unless everyone uses is the one lah. Okay. Okay, but I see that those are obviously simple ones. I'll just skip past. Okay, T2, T1 adjacent resistors 1 meter apart. Receiver area in the middle between them. Okay, wavelengths of 3 cm. At R, okay, at R, right, is at maximum. Okay, but once you move to the side, once you move 0.75 cm, right, this hits the minimum already. Okay, so here, right, remember when you have two sources like this, two sources that are coherent, right? You will, and of the same, they are basically the same signal. So they will give you, that means the data is coherent, same wavelength, same amplitude. So what I have between them is basically you're going to have your yeah, I can draw this well. You're gonna have your stationary wave law. Okay, so at center here, right, it could be just nice, oh, because this is R, right, this is at maximum equilibrium lah, maximum amplitude. But shift down to here, you shift to a node. It went from anti-node to node. Okay, so you look at this wave here, right? Okay, so remember they told us the wavelength is 3 cm. So it means if you go from here to here, this distance here, like that, is 3.0 cm. Okay, which means a 0.75 cm, right, corresponds to lambda over 4. Quarter of wavelength. Quarter of wavelength is just nice, right? From a node, from an anti-node to a node, lor. Okay. So for this question, I think it's good to do some calculation. Okay. Go and work out since, okay, so basically you can say that, okay, let's try the right answer here, 3 marks, right? So you can say that stationary wave is set up. It's set up, right? Set up between two sources. Okay. Then you can say that 0.75 cm is 1/4 of lambda, which is the distance from anti-node to the immediate node. Okay, so you are saying now you move from an anti-node to node, okay? Then hence, as receiver is moved from A to N, right? Signal drops from maximum at A to 0 minimum lah at at a node. Okay, so let's double check. I think this one should be fine. Yeah. Okay, so mention the wave. Okay, I think this one also give a bit more detail in terms of how to form a stationary wave law. But I guess there's some more or less the same, I guess. Okay. Show some little bit of calculation, then it'll be easier. Can draw a diagram like that as well if it's easier to help you explain what's going on here. Okay. I'm gonna be too slow, I think. Let's try. Okay. So half. So right now, now I have okay. So I rotate. Okay, so right now I rotate this guy halfway now. Okay. Here, be careful. They never say it's sound wave. So no, it's sound wave. Because sound wave, there's no polarization involved. Because they specifically say that this is a receiving antenna. Okay, so I would just assume that this one is just EMO. Okay, even though this style looks like speakers, is not. Okay, so going back to here, that means now one source comes like that. One source is in this direction. The other source is in this direction. Both of them have the same amplitude. All right. So then signal at R. Okay. Signal remains the same when R is moved 0.75 cm to a tranche. Okay. So we are doing the same thing. But now they say, oh, at R, right, I lose half of my intensity. At move 0.75 cm, right, my intensity stays the same. Okay, what's happening here? Okay, so at R, remember, R just now was an anti-node. Okay, so this one here, anti-node, right? Both of them at R, right? They're both in phase with each other. They are both in the same plane as each other. So the addition is just A plus A. Then you will get the value there, right? Okay. But now here, right? This one is not the same. This one at R, right, you have one that is vertical, one that's horizontal. So the addition, right, is not so straightforward. Okay, so let's draw it out. You are trying to, okay, let's say this is the equilibrium position. You have A this way, and then you have the second A this way. Okay, so for this now, this becomes a Pythagoras theorem. Your resultant is actually this guy here. A, let's call it AR lah. Okay, so AR here, right, is equals to A square plus A square square root. So it becomes square root 2A. Okay, if you square root 2A, right, then remember your I is proportional to I not, proportional to A square. Or proportional to A square. Okay, so you want to find your new, okay, you want to find I capital R, right, versus the original I. This is equals to square root 2A whole thing square over A square. Okay, so your IR is 2 times of I. Okay, which was compared to the first case, first case was 4 times. Because first case is A plus A. First case, no problem. First case here, right? This one, the new amplitude, AR here, right, will be equals to A plus A. So you get 2A. So your I becomes 4 times of the original. Your IR becomes 4 times of original. Okay, without the squares, right? What I'm doing. Yeah. Okay. So you lose half. Okay. So this is why at R, right, your intensity is half. Okay, then you move 0.5 cm, signal remains the same. Okay, because now there's no cancellation. Because when you move to the new position, right, at the new position, right, your source, one of it is like this. Okay, the original is like that. The other one is nothing really. The other one is like this. Okay, there's no cancellation involved here. Okay, 2, 3, 4. Yep, try and answer for this one. This one's quite interesting question. Okay. Yeah, they actually didn't even talk about the zero part. Okay, do I need to talk about zero part actually? Let's see. Let's read the questions again. Yeah, I would say I want to talk about the zero part as well. As in it does not cancel because this one my my problem with that the JC's answer key that is too brief already. This was JC1, right? I think this is the ACJC question, if I remember correctly. Yep. Okay. So this is it for this one. Or still got one more. Okay. So this one, okay, so you have red light to violet light, right? Okay, you're passing through a grating. Center is white because center is where all, okay, remember this formula d sine theta equals to n lambda. If you sub n to be 0, right? Regardless of lambda, your theta will become 0. That means all the different wavelengths will have a central bright fringe. That means here, right, you have basically all the colors from violet to red. Okay, so you're gonna have a central bright fringe here. Okay, discuss range of distances for x from determine the range of distances from x for the first order observed lah. So for this one, okay, I'm not gonna do it for. I think it's quite straightforward lah. Okay, the only thing here, this is a 200 lines per millimeter, right? So your d here, right? D is 1/200 times 1000. Be careful for that. Okay. Okay. Range of distances from x. Okay. So you want to find the one based on the formula, right? The one that bend the most is the larger angle one. Your lambda equals to 700 nanometers. And then, so your range of 400 to 700 nanometers, right? So go and work out. So go and do sine theta equals to n lambda over d, right? Go and sub this to be 700 and then sub for 400. Okay, find the range of your theta. Once you find range of theta, right, then you have distance from screen, right? 3 meters. You know that this is 3 meters. you can find, let's say this is theta violet. Okay, then the next one, let's say over here, this is theta red, right? Then go and find out what is the distance here. Okay, this one use your sign to go and calculate. Yeah, I won't talk about this one. Okay, show your calculation whether the third order fringes overlap with the second order. So remember your fringe basically starts like this. The center line, okay, let's draw this one. Center is here. So you start off, right? You will have violet. This is V1 first. Then you have red one. Okay. So in the middle here, right? In the middle here, you basically have from violet to red. Okay, but you go on further, right? You will have another violet, let's say somewhere here. Let's say V2. This is V2. Then you have R2, like that. Okay. To see whether your third order fringes, right, overlap with the second order fringe, right? I will compare the larger second order fringe versus the smallest third order fringe. So for the smallest, because if you just imagine, if this one is shifted in towards here, it means my violet line is here, right? Then you overlap with this one. Okay, so I'm comparing angles. That means for third order, I use violet. Okay, for violet. Okay, then for second order, I use red color. Okay, so I'm comparing, say, theta for V3. Is it larger than theta for R2? Is it larger, small? Oh, smaller, smaller. Okay, smaller. Okay. Actually, the calculation, you don't have to work out the RD one. You can just sub in the numbers. I just show you how to do it very quickly. So again, we go from same equation, d sine theta equals to n lambda. I'm comparing theta, right? So I go sine theta equals to n lambda over d. Okay. Then you can see that, okay, I just need to do some partial substitution. I'm just comparing, okay, the d is not important. The one that's important is these two terms, n and lambda. Okay, so for violet 2, for violet 2, 2, right? Violet 3, right? Violet 3, that means I'm doing 3 times 400. Okay, let's write out nicely. Okay, so my n lambda becomes 3 times 400 equals to 1200, right? Okay, then my red 2, my n lambda becomes 2 times 700, right? I think they give 700, right? 700. 700, which is 1004. So since 1004 is larger than 1002, right? I expect for rate 2 my theta to have a larger value. Okay. So going by this two, right, I can know that theta R2 is larger than theta V3. So you overlap. Okay. Yeah. I pause, drink water for a while first. Mm. You got things, just type and ask, or unmute yourself and ask, whichever is easier for you. Okay. Yeah. Mental break. Okay. And SHM. I actually like this kind of question. This kind of question quite interesting. As in it becomes uh a lot of your mechanics involved lah. Okay. Okay, so so I have a test tube that's loaded with small ball bearings is able to float upright in the water density row. Bottom of the test tube is H from below the surface. Okay, so just ignore the rounded bottom, treat it as a square base. That means you can treat it like this. You can assume it to be like that. That's fine. So it's a cylinder there. Lor. Okay. Then draw the forces acting on the system of the test tube and ball bearings when it's floating. All right. So you will have, okay, so here you have on the test tube ball bearings. Okay. Then this one here. Okay, so you will have weight of test tube, okay, plus ball bearings. Okay, so write in full okay, regardless. If it's messy, right, you can write, okay, you can write W here. Write W here, then on the side say W is the same thing. Right, do a legend. Okay. I have a feeling that when it comes to actual marking, they won't be so strict as long as you use terms that are quite standard, like W for weight. But you should also say weight of what lah, because this one there are two weights involved. Okay, but if you short form, I would think they will give chance, but for safety, right, I'll just write in full. Okay. Then of course you have up thrust over here. Because it's floating, right? Make sure that you try to draw the arrows such that they are same length. Okay. So this is up thrust due to fluid, due to water. Okay. So make sure that these two arrows are the same length. Very important. Okay. In fact, the answer key, if I remember correctly, say draw to within like a few of difference. Because this one you can draw very precisely. Okay. Some you might prefer to draw the up thrust here, that's fine. But again, think about neatness, as in is it clear enough for you or not? Okay. Okay, next calculation. Test tube is displaced vertically downwards by displacement y and then release. Then taking up downward to be positive, ignoring any dissipative forces, show that SHM is given by A equals to this equation here, and this is a plus sign, I think. All right. So, okay, so once I push it down, right? Okay, let's draw this diagram now. Okay. So at first it's floating at this height. Okay. So here you have W, you have U1. Okay, so U1 is equals to W when this height is H. Okay. You push it further down. Okay, the tube got longer, but you get the idea. Okay, this is H. This is Y. Okay, so now you have U2 and W. Okay, so first case, U2 has to be larger than W. So you have an upward force. Right? So here, you write the equation first. Okay, you want to find acceleration, right? So let's solve the equation first. We always have to start off from net force. F net equals to MA. So you have F net MA. For this thing, F net here, right? U2 minus W equals to M plus M times A. All right, this is what you have. All right. U2 here. Okay, because I know that. Okay, I know that U1 is equals to W. Okay, so I can go on to sub. Okay, I can do U2 minus U1 equals to capital M plus small m over A. All right. Then up thrust, right? Remember up thrust formula? Up thrust is U equals to rho VG. Yeah, rho VG, right? Yes, rho VG. Okay. V is the volume of this space weight. This one I can further expand. This is rho times the height times Yeah, I think my call got cut off halfway. Yeah, I need to. Is my recording still? Oh, my recording still going on. So weird. Does it work? Okay. Can everyone see? Sorry, I think just now I got cut off halfway. Can see, okay, sorry about that. Okay, so my U is equals to rho HAG, where H is a height, lah, right? Okay, from there, I can go on to write some more stuff. Okay, let's do a side here. Okay, U1, okay, U2 is the deeper height, right? So I can basically write this as rho H plus Y AG minus rho H AG, okay, equals to M plus small m times A. Okay, then look at this one, right? The H term will cancel out. So you have rho Y AG equals to M plus M A. Okay, now we can already find A. So A is equals to, shift the M plus M over, right? So rho A G M plus small m times Y. Okay, where does the minus sign come from? There's a minus sign somewhere here. When I did it yesterday, I could still have the minus sign. 2 minus U1 U2 minus W. Upwards is positive. Minus when I sign go to rho HAG. Yeah, downwards as positive. Is this not positive? Oh, taking down is positive. Okay. So yeah, so that means this equation must change. Let me cancel. Okay. So this one needs to change. This will be W minus U2. So this will be U1 minus U2. So this one will be, and this one will become, okay, this one will be right now. This one. Something weird about my connection is cutting off at times. So I'm not sure how. I think maybe I exited times. I don't know. Okay, so let's rewrite this line here. So this one will change. This will change. So will change now, right? So this is rho H A G. This will be rho H A G minus rho H plus Y A G. The whole thing here will have a minus sign lah. Okay, so a minus sign here. Then this one need to write clearly that this is a times and not a minus. Yeah, that it's a minus sign here. Okay, so once you have that, right, then you see, oh, actually this whole thing here, right, is what you want lah. So A equals to negative rho AG M plus M. That's why. Okay. Okay. This one, the second thing is interesting. I don't know if you can spot it now. Remember we talked about SHM equation, right? The basic form is A equals to negative omega square X. Okay. So you check this equation here, right? This equation already fulfills the form. Okay. So A equals to negative omega square X. So this is your terms. Okay. Yeah. So even if you don't know how to do the first part, right, you can jump on to do the next part lah. Okay, show that the period of oscillation is 0.50 seconds. The H equals to 0.0 meters. Okay, so what else can you do with this? 0.0 meters. You want to find period rho A G M plus M. Okay, how did I do this? I don't remember how to do it. Just did it yesterday. H is should the pronunciation is rho A G. I think go from this guy. W equals to rho A G H. Then go and find height. Where I can't remember how to do. Yeah. What do the answer key for this? Question. Yeah, start from here. Pi t square A H rho G. Okay. Let's try. I think can be done now. Okay. So we have this one here. Then this is I think you sub as M plus small m times G equals to rho A G H. So can cancel away the G's. Okay, you have M over M. So capital H, sorry. Not small h. Capital H. Okay. Then you go and solve. You rearrange to fit into this form. So you have rho A over M. Okay, so you want to fit to this version here as much as you can. All right, so you form this as rho A over M plus small m equals to 1 over H. Okay, that means if you multiply a G inside rho A G, actually you can don't cancel the G lah. So it's G over H lor. Okay. So that means now, okay, so since rho AG over M plus M is equals to omega square, and this is equals to G over H lor. Okay, then go and solve lah. So omega is equals to 9.81 over 0.062 square root. Okay, then this is equals to 2 pi over t. And go and solve for t. Okay, go and solve for t for this one. Okay. Okay. So now you have maximum vibrating energy. Okay, so this is your oscillation. This is your amplitude from just now. All right, so you can sub in the values. Okay, you know omega already. Okay, so omega is equals to square root rho AG M plus M. Square root rho AG capital M plus small m square root. Okay, then my maximum displacement, my amplitude, right, is equals to y equals to 0.01 meters. Okay, let's sub in. So KE max equals to half m omega square x naught square. Okay, so this one will be this m here. So half capital M plus small m omega square x y square. Can go and sub into solve. Okay. So this one not easy lah. I find that the math here, okay, the concepts here are a bit more challenging. We got chat. I didn't see the chat. I'm lagging a bit. Yes, I think my internet connection a bit siao already. Okay, or it's a bit of beat rot lah. I don't know what's happening here. Lagging in terms of voice or in terms of the screen? Both. So okay, I'm gonna off my video. I wonder if it helped the situation. Okay. All right. So you have now you're supposed to draw the graph. Okay, but is it still watchable or not? Is still watchable. Can make out what I say? Yes. Tobias says okay. Okay, so we make do first. Okay. Yeah. No, last time when I started this COVID HBL thing, the first platform we used was Discord. This Discord very good voice quality, but then the video that time was a bit cui. So now I think it's a be better. But I think now everyone is using Zoom, so go with the flow lor. All right. So anyway, we have the period is 0.050 seconds, 0.550 seconds. And then we're going to hit, we start off at where? The question for drawing this graph is that, okay, we know that this is one period. We know that this is one period. In one period, right, your oscillation will go, okay, let's say your oscillation starts at here, right? It goes up, back to down. This is one oscillation. But so that means I need to hit peak twice. I need to hit maximum speed twice. Okay? And therefore maximum KE twice. Okay, but the thing now is that for questions like this, right, you need to ask yourself, where are you starting from? The oscillation started from when you put it downwards by Y. Okay? So if you were to plot a graph of, it's good to look at the graph of your displacement first. I'm just going to draw it very small here. Okay? So let's draw it this way, like that, right? So this is positive Y. This is negative Y, all right? I pull it down first, ma. So I pull down first, right? I start from here, I start from here. I go like that. This is 0.50. So I start from the negative amplitude because I pull down. I pull down, I release, right? Then it will go back to zero, then go up to maximum amplitude. Once it goes up to maximum amplitude here, right? Okay, remember here we can write down here. So at the bottom here, up thrust is more than weight. Therefore, the net force is the acceleration is therefore upwards. Here, at this point, U equals to W. Okay, so acceleration is 0. Here, U is less than W. So up acceleration becomes downwards. Here, U is equals to W. Acceleration is 0. Okay, so you can see that from this simple sketch here, right? At my equilibrium, my acceleration is always 0. At the highest point, my acceleration is maximum downwards. Lowest point, acceleration is maximum upwards. Okay, so this is all in line with your SHM concepts. Okay, so then from here, once I have this graph, I realize it's very easy to do this. Okay, that means when I do my KE graph, right? KE I start off at maximum amplitude. At maximum amplitude, right? Maximum negative amplitude, my velocity is 0 because it's the turning point. So that means my answer here should start at 0. Okay. Then at the center, at halfway through the period, right? It is over here. It is over here. So again, it's now at the maximum positive amplitude, right? So halfway point, it should be 0 as well. Ending here also 0. Okay. So the peak has to occur here. Okay. So for this one, the way of drawing is because usually because once you square a curve, right? We get it to become a concave curve lah. So the whole thing becomes kind of like that. Okay. Like that. Okay, like this. So it's concave inwards. Then do 2 cycles, right? Because they give you the 1.0, so do it twice. Okay, so up and down, up and down. Draw any neater than what I do lah. Okay. Then do we need to because you calculated the value from the previous part, right? This value here, go and write down this value here. What is the actual value? Okay, write actual value. Okay, okay. Do I need to move on? Next one. You have this is basically your critical dead damping. Your damping. Okay, energy is lost through your usual suspects, your drag force. Okay. Then next one is more interesting. Sustain the oscillation, low amplitude waterways of variable frequency are generated on the surface of water. So now I'm using the surface of water as the driving frequency for your water. Okay. So I want to draw the variation with driving. So this one basically you have to draw your standard graph. Okay, so amplitude, driving frequency, it goes like this. Okay, let me check the values. This one I just want to double check. Okay, so like this. All right. Then your standard frequency is at 2. This is your natural frequency because this corresponds to T of 0.50. Okay. Okay, so back to my original one. Over here, I just touch it. Touch it right now. Okay. So this one will be 2.0. Okay. So when I use water wave or frequency 0.30, it is found that the amplitude of the resultant oscillations are rather small. Small here means that you don't have resonance. Okay. Because right now it's 0.30 hertz. Okay. So without changing the frequency of the water waves, suggest reasoning how the amplitude of these oscillations may be increased. So increase means that you want to have resonance. To have resonance, right? Your driving frequency must match your natural frequency. Okay. So now you have to change the natural frequency of your wave. You want to change the natural frequency of your oscillation. So at first, your natural frequency was 2 hertz, right? 0.50 seconds period. You need to slow it down. Okay. How to slow it down? Go back to this original question here. Okay, let's write so we have rho AG m plus m, right? Okay, let's write the bottom. Right. So my amplitude is equal to rho AG m plus m square root. Okay. If I want to drop my my frequency, that means my omega has to drop as well. Fastest way to drop omega, increase m plus m. Okay, so this one means you load more ball bearings. Okay, so when you increase the mass here, right, that means you up this guy. Okay, this whole thing will drop. If this drops, this also drop. Okay. 10:30 already. If anyone needs to go off, and go off lah. Okay, otherwise I'll just finish up this is the last part right? Last question, I'm not talking about it. Okay, I hate polarization, but let's do it. Okay. Polarization. Okay, so this is a long question. I think this is part of this is only part A. So I think this is a 20 mark question, I think. 20 marks. Yeah, it goes on for a long time until here. Okay, so light intensity, unpolarized light I not incident. So this unpolarized. Unpolarized, let's just mark it as unpolarized. It's this way over here. After polarization, it should become like this. Okay. Unpolarized, polarized. Okay. Then I place a second filter parallel to F1. So again, this has the same polarization. Okay. So completely polarized strikes F2 and 90 degrees surface. So there are some numbers here that are very interesting. Huh? This is basically saying that it is reaching the plate as at this normal. Okay, it's reaching at the normal. Okay, so basically the light is just telling you that okay, if the top view of polarization plate is like this, right? The light is coming in like that and not like that. That's all they're saying. Okay, so don't get too confused by it. Okay, so if I have them polarized, right, the intensity here, intensity after F2 should still be the same. So it should have the same intensity because you see, this position intensity is equal. The light that emerges from F2 is the same as incident. That means if because they have same polarization, right, the second polarizer F2 does not stop any of your this wave. All right. So now I rotate to 90. Okay, rotate to 90 degrees, right? Then once I rotate, then of course I'll have variation lah. Okay. So I naught. Okay, let's see. I naught was the original one. I naught was original. So don't be tricked. So passing through the first polarizer, right? You will lose some of the energy already. Okay? You will lose half of the energy, I think. I never remember. Okay, what's the question? Yeah, you start off at half the energy already. Okay? So this one is not an I, so I think this is the main trick here, because here you start off at, this is I naught. Okay, this is I naught intensity. But once you half it, right, it becomes, once you pass through one polarizer, it becomes I naught over 2. Okay, so then now you start to draw lor. So you are trying to draw for what is the intensity after F2, right? That means you're starting at, if it's at 0, it will be at parallel, right? So this is parallel. This is also parallel. This is perpendicular and perpendicular. This is parallel. Okay, so you start here and here and here. So your wave, this is a sine curve, right? So it kind of goes nicely like this and like this. Okay, something like that. Okay. Okay. Next, F2 rotated until no light emerges from it. Okay, so no light emerges from it. So I know that. Okay, so again, I draw in my wave. This is at first like that. Polarization is like this. Come out from this guy is like that. Then now I go, this is like this. So come out from here, nothing. Nothing is here. Okay. Okay. So then I come out from F3. There is the light that emerges from F. Okay. I place between F1, F2. My mistake. Okay. So yeah. So I need to undo some stuff. Okay. So this guy is the one that is right angle. So F1 is perpendicular to F2 lah. Right? Then I place okay, F3 is equal in intensity. Light that emerges from F3 is equal in the intensity to the light that's incident. That means this guy, after F1, right, the polarization becomes like that. Okay, but F3 doesn't do anything to stop it. So F3 is still like that. So that tells you that F3, right now is parallel to F1. Okay, so it's not doing any cancelling. All right. Okay, so then now F3 is rotated about 45 degrees from an axis to its surface. So now the setup becomes this. So your F1 is like that. This is F1. Your F3 goes like that now. F3, 45 degrees. Okay, then your F2 is still like that. Okay, so explain now why some light emerges from F2. Okay, when you pass through F1, right? You pass through F1, you have this amount of intensity. At the start, you have this amount. Okay, after passing through, you have this because it's polarized. Okay, then F3 is diagonally polarized, right? So some of it will come through this way. Okay, then now you want to take this diagonal polarization, right? Pass it through F2, which is horizontal. So there is a component of it that is horizontal, you see? There's some part of it that's horizontal. So some of it will come through to the other side. Okay, like that. All right. So for explanation, I'll just refer to the handout here. So again, it's about the angle lah, right? So you will have some light coming through as long as your wave, the polarizing plane and the polarization of light is not at right angle. Okay, so it come through. Okay, so F1 is, after F1 is vertical, and then F3 is at 45 degrees, right? So some light will end up going through between from F1 from after F1 to after F3. Some will go through. So when it comes out from F3, right, you'll be at an angle lor. You'll be at an angle like this. Okay. Like this one here. Okay. So again, now if you compare this angle versus this angle here, right? Then again it's not right angle, right? So it can be polarized, comes out this way. Okay. So last one is just a calculation, intensity, right? So we can do we start from I1. Okay, we want to find I3, right? So if you write out this one, the final one, right? I3 is equals to I2 cosine square, cosine, I can't remember again. Cosine square, okay? Cosine square 45. Okay, so cosine square 45. Okay, this is between this is going from, sorry, I2. I2 is the one that's coming out from F2, right? So you look at I3, cosine square 45. Okay, then I know that I3, right, is equals to I1 cosine square 45 as well. Okay, and then I1 is half of I0. Okay, so I sub in, no? Okay, so if I do it that way, I can try lah. Okay, so this one goes on to I3 equals to half I0 cosine square 45. Okay, then go on some more. I2 is equals to half I0 cosine square 45. Outside is a cosine square 45 as well. So you have 0.5 I0 cosine 445. Okay, go and solve for this. And that's it. Okay. Anything else you want to clarify? No, we can stop here. It's 10:36, which is nice. Okay. If not, I'm gonna stop recording. We can call it a day. If you want to ask any other stuff that you think is personal to you, then you just stay and ask lah. Okay. Can. Otherwise, is this part recorded? Oh, it is. Okay, stop recording. Okay. Otherwise, we can stop here already.